So, we were talking about, right, how the laser beam, right, propagates. So, propagation is along z direction. Okay, it is, why it does not write? Oh, okay, it is along z direction. Okay, propagation. So, when beam propagates, as I told you, at the beam waist, right, z equal to 0 position, it's right, you can see that it is a plane parallel, and then slowly the radius of curvature comes into picture. Okay, so it goes to, right. So, it is a combination of plane parallel and circular wavefront, and at z equal to 0 condition, if we cut across, right, the beam, what we see, this beam, if we cut across, it is a circular beam profile, approximate circular beam profile with a Gaussian beam distribution. And Gaussian beam distribution means, let us say I0 is the intensity, right, I0 intensity at 0. So, at any, right, other point along x or r, it is exponent of minus 2, right, r square upon w 0 square. Okay. What is w 0? W 0 is the beam waist at the point where intensity becomes 1 by E square, is not it? When R becomes W 0, intensity is 1 by E square, is not it? So, I R becomes I 0 divided by E square, is not it? So, that position of R is nothing but W 0, okay, that position, and that is the in terms of radial distance, okay, beam waist. And as we go along this, right, z direction, what we observe, that this W 0 beam support size changes. Okay, this beam support size changes, and that is given by, at any point z, okay, at, let us say at any point, say over here, let us say z, okay, then W z, okay, is given by W 0 1 plus lambda z by W 0 square is 1 by 2, okay, it is given by this form. So, as z increases, right, W z will keep increasing, okay. And right, we also learnt that when this W z becomes root 2 times W 0, okay, that position of z, okay, that position of z, which is nothing but the Rayleigh range, the Rayleigh range, okay, it is ZR, okay, or Z 0, in this case it is Z 0 or Z 0, right, is Rayleigh range, where W z beam support size is root 2 times the beam waist W 0, okay. That means area becomes double, is not it, pi r square, the total in area of this Gaussian, right, beam, circular wave, right, beam becomes double the beam support, beam waist area, okay. And this is Rayleigh range, and double the Rayleigh range is known as confocal parameter, confocal parameter, okay. Okay, which is we derived it approximately, right. Confocal parameter is not approximately, but equal to, somewhere I did, I would, okay, pi w, so 2 pi w square by lambda, okay, by lambda, okay. That is the confocal parameter, okay. So, that is what we learn. Now, Gaussian, see now this divergence angle, okay, can be estimated, right, at by of course, this divergence may be small. If the beam sport size is large enough, the divergence may be small, and this divergence angle, half of this, right, theta by 2, can be estimated by approximating it as a triangle, right. So, this is when z tends to infinity, okay, we can estimate right, opposite side divided by adjacent side, right, is nothing but tan theta by 2, is not it. So, when theta is small, we can represent it by tan theta by 2, which is approximately theta by 2, which is opposite side, which is nothing but the beam sport size at this position z, right, divided by adjacent side, which is z, is not it. And then this theta can be estimated for limit z tends to infinity, okay, z tends to infinity to very large distance, right. We are approximately finding out the divergence by approximating it to be linearly increasing, okay. So, limit z tends to infinity w z by z, and from this we can derive the divergence angle. So, theta by 2 is lambda by pi w z, okay, and total theta, total divergence angle is 2 lambda by pi w 0, okay, 2 lambda by pi w 0, correct. Total divergence angle 2 lambda by pi w 0. See, you can see if the wavelength of the electromagnetic wave is large, the angle of divergence will be large, okay. For the same beam waist, okay, with two different wavelengths, let us say lambda 1 and lambda 2, they have the same beam waist, but the divergence angle will be different, okay. With longer wavelength, right, divergence angle will be large, okay, one thing. Secondly, if the beam waist is larger, the divergence angle will be smaller, okay. That means, if I have a larger beam diameter, beam waist, sport size, okay, right, this beam waist is much, if it is large enough, the divergence angle will be slow, very small, okay. That is, see, it's and when I have a very small beam waist, the divergence angle will be large, okay. So, that you remember. So, when a Gaussian beam is focused to a very small size, right, beam sport size very small, then the divergence angle will be large, it will diverge very quickly. The confocal parameter, right, will be very small, right, because w 0 is small, so it will immediately diverge. So, right, beams will widen, right, keep in mind all these aspects, very important, right. That is why if I want to use a beam with a very less divergence, I would use the beam waist such a way that I will engineer the optics such a way that the beam waist is minimum sorry maximum large enough, so that the divergence angle is controlled, it is controlled to certain extent, okay. So, indirectly we can control to certain extent the beam divergence, etc., in with laser, in case of laser beam, okay. By controlling its beam waist dimensions, etc., we can control the beam divergence, beam confocal parameters, etc., very well, okay. So, that is a very important factor, okay, that we now know. So, what this confocal parameter tells us, that what is the depth of focus. Let us say there is a layer, I focus the laser beam on the top surface, but if the beam focus is so small beam spot size, the divergence will be large, the confocal parameter will be small. So, the intensity will immediately will change, correct, very quickly it will change as it travels. Okay, maybe I will, what I am trying to say, that if there is a laser beam and we focus, okay, using a lens. So, confocal, so this is convex lens, okay, we focus the laser and it will get focused, okay, and this will be W0, correct, small size. However, if this size W0 is large enough, the divergence will be small, the confocal parameter which is right given by 2 pi W0 square by lambda will be large, okay. Divergence angle which is given by 2 lambda pi W0 right will be small, etc., right, if W0 is large. But if I focus using right this same lens, but let us say if the beam size is much larger, let us say I should have drawn with larger, let us say if the beam size, if the convex lens is this, beam size is larger, then the focusing right will may go like this, okay. Let us say same maybe like this, okay. So, if this W0 for red color, no, W0 is smaller than for this, right, black color, this line and this Gaussian beam, what will you see? Confocal parameter B for red color will be B for right red color will be confocal parameter will be smaller than confocal parameter, okay. So, okay, will be smaller than the confocal parameter for right if this is B, okay, confocal parameter, and the divergence angle for red goes will be much larger than the divergence angle for this, okay. The confocal, and this indirectly confocal parameter gives us depth of focus, okay. So, we can assume approximately within the confocal parameter the beam remains focused, that is what we can assume, okay. But in case of red color this beam, the depth of focus is much smaller, confocal parameter is much smaller, while with black color this beam the divergence is small, confocal parameter is large enough, the depth of focus is large, okay. I can focus the beam within that beam, wherever workpiece is there, approximately I can assume that the intensity is same approximately. Of course, as per confocal parameter definition, the beam size becomes double, is not it, beam spot radius. So, area becomes double. What is intensity? Power divided by area. So, if area increases, automatically intensity will change, but we are assuming within the confocal parameter the W is not increasing so much, beam spot size. So, intensity is approximately the same, okay. So, that is our assumption, right, approximately. So, that is the case, okay. So, these aspects we should remember. Now, one more parameter comes into picture, which is corresponding to the real beam, okay. So, whatever we described the Gaussian beam, right, ideal Gaussian beam as we discussed, W0 is given by W0, right, 1 plus lambda z divided by pi w0 square, this, okay, this, right, confocal parameter, okay, theta is 2 lambda, sorry, pi w0, okay, theta full divergence angle, correct, full divergence angle. Okay, 2 lambda by pi w0, okay, okay, anyway, so that is right, full half divergence is lambda by pi w0, anyway. Now 2 lambda. Now in actual practice, real beam, case of actual practice, real beam, since, right, it has different modes. Now I am going to talk slightly differently. We know about longitudinal modes, correct, frequency, axial modes. Similar to the longitudinal modes, there are transverse modes, but not in terms of transverse modes does not represent frequency, etc. different. Transverse modes are because of the cavity configuration as well as the amplifying medium configuration, etc. Okay. So, for example, just to give you an idea, right, let us say if there is a flat, right, mirror, there are flat mirror, this is amplifying medium, we pump this medium, then lasing action starts, and we know that propagation of direction perpendicular to this flat mirror will be the actual, right, and accordingly the output will be obtained, right, that is we already learned. Now instead of this, if I have something like a spherical, right, hemispherical or spherical cavity, and now you see the light amplification mainly will be in this direction. Okay. However, the light amplification can be, okay, by a small, very small, can be like this, can be like this also, okay, it can be like this also, okay, and it can be like this also, you understood, small angular deviation is there, but still it can form, right, a cavity, this, okay. So what will happen, the intensity distribution will be different in this case, it is not Gaussian. Over here if amplification starts, the laser will start, and theoretically you can consider this as something like a, right, a cavity, maybe laser beam, right, will be, right, it will be, and then it will propagate like this, okay, with a Gaussian beam over here theoretically, but over here one beam in this direction, other beam in this direction, and this. So basically the laser beam characteristics, what you will see here will be a combination of all these waves coming into picture, right, transverse. So these are all transverse waves which comes into picture, okay, and the beam intensity distribution is different, okay. If I cut through, the intensity distribution may be, okay, maybe I should, right, intensity distribution may be like this, I do not know, I am simply trying, while over here the intensity distribution may be, right, like this. It depends upon, right, how the intensity is distributed across. So this type of distribution, etc., is very difficult to predict depending upon cavity configuration, depending upon amplifying medium, etc. So the real beam, okay, is represented by theta real is represented by a factor m, okay, which represents axial mode some distribution, and very difficult to predict that, but we can represent equivalent to m theta ideal, okay, theta ideal, okay, as well as w 0, okay, beam support size, okay, maybe zero is m times real, right, actual the ideal beam, okay, mw0, okay. So, this is our definition, okay. What m represents? Basically there is a factor known as m square factor, okay, m square factor. This factor, if it is 1, okay, which represents m equal to 1, and theta real will become theta ideal, correct, and w 0 will be equal to ideal beam waist, okay. But for most of the real beams, laser beams, etc., m square is not 1, it is generally greater than 1, okay. Value is slightly larger, maybe 1.2, 1.3, depending upon the laser cavity, etc., all configurations, okay. So, this factor, now this m square is based on theta real into w 0, okay, I said when I say this w 0, this is real, okay, real beam, okay, w 0 real is equal to m square theta into small, okay, and what is theta? 2 lambda by pi w 0. So, m square to 2 lambda by pi, correct, okay. So, this is this m square value, right. If it is 1, it is ideal beam characteristics. If it is more than 1, there are multi modes hidden in this cavity laser system, etc. We cannot find out individually, but we are representing it by a parameter m square, okay. So, most of the laser systems what you will be using, okay, for your applications or anywhere, right, wherever if you apply use, they will have some m square value, okay. It if it is nearer to 1, it is very nearer to the ideal beam things, okay. You will be able to predict its propagation everything very easily, but if it is not nearer to 1, larger than 1, maybe 1.2, 1.4 or 2, the beam characteristics accordingly will little bit different. But this parameter m square helps us to quickly estimate approximate beam size, etc., similar to the Gaussian this distribution, okay. So, this m square is, let us say, in case of a beam which is right, which is expanding, not ideal beam with a parameter m square, then w z, the beam support size at any position z is beam waist w 0 real beam waist, okay, to 1 plus, okay, m square lambda z okay. What has changed? When m square is 1, w 0 is small w 0, right, beam space, and same equation as we described previously, okay, nothing different. When m square is different more than 1, this will be the beam, right, this parameter, and with this if you estimate the confocal parameter, whether it is real or ideal case, correct, they are equal, confocal parameter will not change, okay, okay, please, because beam size is also increasing, divergence is also increasing. changing, right. Beam size, divergence both are changing, but the confocal parameter corresponding to that will remain the same. Okay. You remember confocal, I am talking, oh sorry, I should write confocal parameter, confocal, not Z, you will not be able to understand confocal parameter. Okay. So, Z0 real, right, 2 times Z0 no is confocal parameter corresponding to real, it is 2 times Z0 ideal. Okay. So that you remember. What is confocal parameter? Already we described, isn't it? 2 times Z R, 2 times pi W 0 square pi lambda, ideal, right. And the real one correspondingly to this is ideal, okay, 2 times Z R real, let us say real is 2 pi, what is W0? W0 will become accordingly W0 square, okay, divided by m square lambda. Okay. If you derive, you will end up with this formula, okay, and okay, right. What it means? W, so, right, you understand. So, if m square is 1, W0 will become small w0, it is ideal condition, and ZR real, what is W0? M square M0 W0, is not it, right. We have already, right, what is W0? M into small w0, right. So, if I substitute instead of W0 m into the same answer, you will get it, m square will get cancelled. This is for the real. Okay. So, both way confocal parameter will not change, however, the beam divergence, beam waist will change. Okay. So, please remember those aspects. Now, how do we all this whatever we learn, how are we going to use? Basically, you will be using this what we learnt in terms of Gaussian distribution, beam propagation is whenever you are using optics along with lasers, right, you will need estimation how the beam is getting focused, what is the size, etc. So, when I am using let us say a laser with okay, W, let us say here this is the beam waist W0 and there is a lens, okay. Let us say this is 1 W0 1, and if I am using a lens with focal length f, then this beam will get focused, then again it will, right, it will expand, it will diverge, and this focus port size is W02 depending upon f, depending upon this 3 values, this values W0 will be defined. Okay. So, right, W02 will be defined, whether anything is there, any values f, okay, anyway, what is this W02? Okay. So, W02 is nothing but f of theta divergence angle, okay, theta 1, okay, theta. What is theta? In terms of half angle divergence, it is lambda by pi W01. Okay. So, W02 is f into lambda, which is wavelength of the electromagnetic wave. W01 is the beam waist, the laser beam before focusing. W02 is the beam waist of the laser beam after focusing. Okay. Beam waist, I am not talking about beam port size. Okay. Beam waist means this position W0 at this radial distance is estimated at, this is Z equal to 0 position, okay, right. No, I am talking about radial only, so half divergence, okay. So that is why I wrote, maybe I will write here, okay, theta by 2 I will write 2 reduce here, right, where theta is full divergence angle. Is it okay? So, if I know the beam waist, and if, and what beam waist I want to achieve, if I want to achieve a particular beam waist, I will select a convex lens for particular focal length, okay. And remember, the beam support size also depends upon wavelength. If wavelength is long enough, my focusing, right, will not get focused to a very small spot size. If I want to control a small spot size, my wavelength, I mean the wavelength of the light, if shorter, easier to get the smaller spot size. Of course, I fixed wavelength is fixed, I cannot change for my application. In that case, for the shorter beam focus spot size, right, accordingly I will check, I will select the f accordingly, right, or I will select this W01 accordingly, right. I will have a larger beam waist beam size and then use small f focal length, automatically the focus spot size with the beam waist size will be much smaller, okay, for a given wavelength of the electromagnetic wave. Okay. You can have, right, different combinations based on this. Most of the time, of course, you will use this configuration. However, how did I derive this or this formula, I have not shown you, right. It is you will have to go from here, step 1 here, then reach here, then from here reach here. So, there is an approach, Jones matrix approach, in order to derive the beam support size with, right, some calculations are there, matrix approach to determine what will happen over here. But in general, most of the biophotonics applications, we may be limiting ourselves to either collimated beam size or a focused beam support size, etc. So, this is what we will use, okay. And when I was talking about optical fibers, I told you two important things. If it is a single mode optical fiber, then the core radius, okay, or core diameter, but half of that is core radius, will represent the beam waist. Okay. So, if this is a fiber with a core, right, this is core, this is clade, and beam will come out and it will diverge the beam. So, this is W0 beam waist equivalent. So, if this is a single mode fiber, okay, fiber, then this divergence angle is nothing but the Gaussian beam divergence angle, decided based on the beam waist and the wavelength, right. So, this theta by 2 is equal to lambda by pi W01, correct, this, right, what we derived, okay, that is. If it is a multimode fiber, okay, if it is a multimode fiber, so same with the okay 20. This divergence angle is decided by what? It is decided by numerical aperture of the fiber. Okay. Numerical aperture of the fiber will determine, okay, divergence angle over here, okay, beam divergence, multimode fiber. is it okay? So, single mode fiber, the output beam will be Gaussian characteristics, okay, with the beam waist over here, okay, beam support size, beam waist, is it okay, right, and then it will diverge depending upon the Gaussian beam characteristics, while here the divergence will be based on the numerical aperture the fiber, okay, for multi-mode fiber, okay. So, that you remember. So, with this, right, now we know that there are different lasers, different right applications, etc. We would prefer lasers depending upon our requirements. I want laser beam to be absorbed by the tissue, or I want laser beam to be transmitted through the tissue, right. I want to measure certain absorption characteristics of the tissues or constituents, etc. Will decide what wavelength shall I use, so that either I can pass through or I can the beam will get absorbed and right heat is generated, etc. That part maybe tomorrow again I will explain to, because let others be there, but before we go to right that part, again I will repeat that part. I thought today I will start with another topic related to optical sensors. We will try to cover in this couple of lectures quickly what are the different types of optical sensors that we use. Okay. So, case of optical sensors, okay, so which are also known as photo sensors, okay, photo sensors, and mainly of course there are various other approaches, but mainly like photodiodes are used. Of course, we can use photoconductors also. Okay. Okay. Now, photoconductors means basically photon will interact with a particular material to generate electrons, and then those electrons will be conducted and then they will be used. In case of photodiodes, basically light will interact with electron hole pair and it will dissociate. See, when they combine you get a photon, right, energy. Now, it is just a reverse process in right what we talked in diode, laser, optical diodes. Here light will, incoming light will interact with the electron hole pair, the electron hole pairs will get dissociated, and then depending upon the electrical field direction, etc., and right depending upon right what basically electron will move in one direction, photons holes will move, and you will see the flow of potential will be generated and a flow of current. Okay. Now, this photodiodes, when we use, okay, it's a simply a diode, it's a diode, okay, it's a diode which what we use. Okay. However, it is different from the laser optical diodes. What we consider is, instead of a positive bias applied, it works under reverse bias condition. Okay, reverse bias condition, and there are two modes of such reverse biased conditions. Okay, let's okay, this we checked. Okay, this I will describe when we go. Okay, 1 minute. It is there or not? Okay, it's not there. What is there? So, as I told you, when right, photons when they come interact in this depletion region with the electron hole pair, the electron holes will get dissociated and electrons will move towards conduction, holes will move this right towards p type, and basically you will see the current flowing. Now, what band gap energy, let us say photon is coming with band gap with the photon energy less than the band gap energy. If it is less than band gap energy, this electron hole pair will not be able to get dissociated, right, because photon energy is not enough to dissociate them. Okay. So, if it is less than the band gap energy, if the photon incoming photon energy h nu or photon frequency nu is such that h nu is less than E g, which is the band gap, then we will not see, okay, we will not see this electron hole pair being created. Okay, one thing. So, here current you will not see this current flow or right conducts current flow will not be there, no current flow basically, okay, no current flow. Okay. However, if the photon energy h nu is greater than the band gap energy, right, or photon frequency such that, right, it is much larger than this, right, e.g., then what will happen, this energy is sufficient enough to operate, right. So, automatically this conduction will come into picture. However, if you keep on increasing this photon energy, right, what will happen, the absorption becomes so prominent, okay, that the photon energy will get absorbed in a very small layer of this depletion region. The number of electrons may not be generated so many, okay, H, right, many electron hole pairs may not get dissociated because photon energy will get absorbed, it will not be able to travel through the medium for a longer distance. Okay. So, there is a limit on either side, right. So, silicon, if you consider, it has a particular wavelength range within which it will work as a photo sensor. Okay. Beyond a longer wavelength side, it will not work because photon energy is not sufficient to separate electron and hole pairs generate. Shorter wavelength side, it may not work because shorter the wavelength, then the energy will get absorbed in the top layer of this material itself. So, more number of, even if the electron hole pairs are generated there, by the time they travel through this region, they will get diffused, okay, they will not be able to travel. Okay, it will decide the range. We will see what are the ranges for some of those semiconductor based sensors. We use 3 or 4 such types of such sensors. So, we will see that part, okay. And the configuration of this modes of operation is okay, maybe it's 2 types. One is photovoltaic type, conduction type, okay, photovoltaic type, and I think photoconductive mode, okay, not conduction, conductive, okay, I am sorry. Okay, mode of operation. So, in case of photovoltaic type, the diode is not biased, okay, the sensor diode is not biased. So, okay, so we have okay, this is light comes, okay, and we will see ground. RB. This is the general, right. This is feedback is provided for amplification, okay, R2 R1. This is for feedback, right, amplifier feedback is given. So that the output over here V output with respect to the ground, right, is taken care in terms of. So, this is photovoltaic mode. In case of photo, right, conductive mode, we will use of course reverse bias operation, okay, reverse bias operation, and at the same time you will see that the configuration is slightly different. I will just draw quickly, so that then we will think about it. Okay. Light comes, and then okay, what will I have to do? Okay, maybe let's see. Okay, I'll sorry, same thing. I'll redraw little bit space wise. This not available. So, basically in this case there is no DC bias, okay, there is no DC bias anyway, no DC bias, okay. So, there is no question of reverse or right forward bias, anything, no DC bias, and it's just some light falling on this, automatically electron hole pair generated, and when they right get accumulated, the output voltage difference is amplified using an voltage amplifier, and we see the output. Okay. So, this works very well, okay, without any external bias applied. Only thing is there is a limitation in terms of to if there is a very small amount of this thing, no, generation, this part, it or the response characteristics, okay, is little slower, response characteristics is slower, because the capacitive effect of this detector area plays an important role in terms of time constant being increased. Okay. So, RC is very large, okay, for this detector, and because of that the response characteristics are slower. Okay. While in case of a photoconductive mode, it is of course reverse bias over reverse biased in the case. Okay. Uh, and the current flowing through this right circuit will be amplified, and then you see the output V output as right reverse biased output. Okay. So, this approach of photoconductive approach, where right it is biased with respect to right, ground, uh, and then the output is captured. Okay. And the if we see within the, let us say this is a P region, okay, this is N region, maybe this is a depletion region, right, intrinsic and depletion region. Then whatever photons are coming, let us say, okay, they will get absorbed in this region, okay, in this region, and we will apply, let us say, reverse bias, right, and because of this reverse bias, okay, sorry, right, RL load resistor, there is a photocurrent which is passing, and we are measuring the output, correct, V output over here. Okay. So, this is the photocurrent IP which is passing through this. Photons are coming, let us say, and holes are generated, and electrons are generated in this direction, right, holes and electrons are generated, and photodiode, right, please enroll. Okay. So, now this depletion region, right, basically determines how many photons are getting, right, how many photons are useful in generating such electron hole pair, etc. Secondly, when it passes through this depletion region, the absorption of this depletion region, the photon absorption through this depletion region is also determines the photon penetration depth. Okay, penetration depth. So, let us say as intensity, a number of photons, right, which will get absorbed at it passes through this material, depending upon absorption characteristics of this material. Okay, absorption by through the depletion region. Okay, through the depletion region, through the this region will decide, right, how much, by how much amount the light will propagate through this, and it will how much, right, depending upon the depth of penetration, right, as well, right, depending upon the depth of penetration, the diffusion length can be determined. Okay. We will see what it means, because if the depth of penetration is very small, right, then electron hole pairs generated over here, by the time electron reaches to this position, it may get diffused, okay, it will get scattered, diffused, etc. We want electron to immediately cross this depletion region and hole to cross this side. Okay. But if it is the penetration depth is of the light is narrow, then the electron generated within that narrow band will not be able to travel long distance to reach to the end. Okay. So, indirectly such penetration depth, depletion region, etcetera, all they determine, right, the characteristic of this detector, and the reverse bias allows you to measure this current very clearly. Okay. If it is forward bias also, we can measure the flow, because when light strikes this depletion region, the resistance will decrease. Okay. As electron hole pairs are generated, resistance is decreasing, electron hole pairs are generated. So, basically light affected resistance decreases, but then but what happens if it is in a forward bias condition, already there is a current flow. On the top of it, now photo current is going to pass. Now, photo current intensity, the current amplitude, current amount may not be as large, because the photon, let us say the optical radiation intensity may be very small, then I will not be able to measure, right. If there is a very large bias, already some current passing, on the top a small increase in the current is very difficult to measure. But if there is no current passing, and because of the photo current you see the output, it is very easy to measure, right. So, reverse bias is in that sense very useful. Over and above, the reverse bias increases this width of the depletion region. So, indirectly the number of photons interacting will also be increased indirectly. So, it will allow larger output current, etcetera. There are various ways of thinking, but the simplest thing is, right, the depletion region, and basically photon means what shall I say, the amount of photocurrent, right, which you want to measure will decide. So, and another point is with this approach of reverse bias approach and this intrinsic depletion region in between, PIN we say, intrinsic region, I region, but this combination allows better means low capacitance in terms of measurement, faster response characteristics, okay, faster response we achieve. So, response characteristic is also fast because of this PIN combination, okay, intrinsic region. So, with this tomorrow we will continue from here. We will try to see what is the meaning of quantum, means what is the meaning of this detector efficiency, etcetera. What is the what are the wavelength ranges, and how can we make use of such sensors for our applications. Thank you very much.